Hello, everyone, and welcome to the next event in our webinar series. Today is a special collaborative presentation between Thorlabs and Bruker Scientific. I'm Dr. Mike DeArmond, Product Line Manager for Laser Technologies here at Thorlabs, and I'll be moderating today's talk. With us today are Dr. Sergey Shilov, Product Manager for North America Bruker Optics, and Dr. Feng Xie, Product Line Manager of Mid-IR Lasers down at Thorlabs Quantum Electronics. And they'll be discussing applications, limitations in mid-IR, FTIR, and the tools, the laser-based tools for overcoming these limitations and unlocking some new applications. Throughout this talk, please feel free to use the Q&A tool and submit your questions as they come up. The speakers will have a chance to answer those after the presentation. If there are any questions we're not able to get to, we'll have your contact information. We'll be able to reach out afterwards with some answers. With all that said, thanks for joining, and it's my pleasure to hand it over to Sergey and Feng.
Okay, thank you for introduction, and we will start with just describing what are inside of FTIR spectrometer, what are the major components. Well, obviously there is a detector. There is a lot of improvement nowadays for the detector. Its sensitivity becomes very, very high, and then you can put up to 6 different detectors inside the FTIR spectrometer and automatically move between different detectors. So next component in FTIR spectrometer or in interferometer, and one of the major components of interferometer is beam splitter. Also recently there is a lot of advances on beam splitters, and you can get few beam splitters inside FTIR and can do automatic changes on beam splitters, which is allow you to access multiple spectrum range. And the last is source, is also one of the most important components of FTIR spectrometer. So the standard source in FTIR is a globar, which is silicon carbide rod, which is heated at high temperature, emit infrared radiations. Also, you can put NIR source or the visible source. So what are the major difficulties with the sources? Well, the current mid-infrared spectroscopy methods use a broadband globar, as already mentioned. That globar exists for like 60 plus years and basically still the same. There is not much advances. And the reason of this, because physics prohibit this. You cannot make a source brighter by just going to high temperature, because you also shift the spectral range of the source. What also is available now is laser sources. That sometimes we have high optical power, but narrow spectral range. What kind of needs exist for applications and for FTIR world and all the vibration spectroscopy? We need a high broadband source with a high brightness. And one of the reasons why we need it, because if you would like to measure through optically dense media, for example, like aqueous solution, which is water absorbed a lot of an infrared. Another application is a study of diffuse reflection light, which is reflected from poorly refracting samples, for example, like tablets, polymers, and black carbons, cathodes, and the batteries and cathodes and anodes. Another application which is bright sources are needed is a standoff analysis, also identification of chemical pollution in the atmosphere, and also another very big application is microscopy, where the bright sources are extremely needed. So solution for all these problems is combine spectrally broad band source and with FTIR spectrometer. What we have right now in the market. So of course the globar, which as I already mentioned, 60 plus years, there is not much changes. Next is synchrotron radiation. Only in the US, only a few synchrotrons available, but then you need to book time and you go there, and it's very time consuming. So, well, another option is, which is developed a lot in the recent years, at quantum cascade lasers, which is miniature lasers, and emit at mid-IR spectrum range. And also you can get mid-IR supercontinuum laser. That will be discussed on the next part of the presentations. So these two sources, QCL and mid-IR supercontinuum lasers, can be combined with an FTIR spectrometer. How it's can be done. So this is an example of a beam path of our Invenio FTIR spectrometer. And you can see on the left side, on the right side, there is an input for the radiation. So basically, you can bolt your external source to the input of infrared radiation and use it as a source for FTIR spectrometer. These inputs allow you to can be configured as for the parallel or for focused radiations. And as you can see, 2 inputs is available. You can mount it up to 2 different sources. So now let's talk about, can we compare the performance of a quantum cascade laser versus the globar? So what we did for the direct comparison, we bought just a creatine, which is, it's a muscle enhancer. So it's why we choose this material, because it's very easy soluble in water and absorbed in the range where our quantum cascade laser emit radiation. We have QCl from one of our vendors just for test. Okay, well, first things to do, what we did, we prepare about 20 milligram per milliliter of creatine in aqueous solution, and measure transmittance through using 15 micron and 125 micron cell. As you can see here on the red shows the general energy which just goes through 15 micron liquid cell, and below is a 125 micron liquid cell when we use a standard globar source. So water completely absorbs all the radiation from the globar at 125 micron. As you can see, there is very, very little radiation goes through. So now, okay, let's we collected background spectrum without creatine, then collected spectrum sample spectrum with creatine. So divided to each spectrum to each other, takes minus log and get an absorbance spectrum. It's a typical techniques what we do in FTIR spectroscopy. As you can see, with a 15 micron cell, so we can get a very nice spectrum of creatine in a water solution, just water automatically subtracted. And while we do 125, there is nothing. It's just only noise because all photons absorbed by water. Next, we do the same experiment with a quantum cascade laser. And first things to show you how much energy goes through the cells. And you can see here is you can see a very nice signal which just go through 125 micron cell with QCl. So while this comparison when I already mentioned was 125 micron cell, there is nothing passing through. Okay, then we do our standard calculations on absorbance values, and you can see we can get absorbances at 125 micron cell with a QCl through a very nice spectrum, which is what we expected, a very comparable, basically the same spectrum that we measure at 15 micron with a globar. You can see that it shows a different advantage of QCl. Even you have very highly absorbing materials, you still get light through and can get a decent spectrum of material dissolved in the water. So, and Bruker makes us another step further. So it's combined quantum cascade lasers with FTIR spectrometer, and that's the product named Hyperion II microscope. So it's basically a combination of standard FTIR spectrometer with a QCl-based microscope. You can do measurement on both worlds. You can do FTIR measurements on this system, and you also can do QCl-based microscopy on the same system. It also can do all the infrared imaging, and you also can do all the type of spectroscopy. You can do regular, you can do reflectance, transmittance, or ATR spectroscopy. Let's talk about how this QCl works and on this system. So what we do, so that's we use QCLs and we use a grating, so we can tune the grating to the specific wavelengths emitted by QCl and collect spectra of this wavelength, and then we can change move the gratings and select different wavelengths and so on. So basically we can do sweep scan to cover all the spectral range of QCl. So We also can do imaging on this microscope. So what is infrared imaging? So what we do, so again, we tune our QCL to the specific wavelength and scan all image of our sample in X and Y, measure in X and Y direction and create an image of sample at this particular wavelength. Then we also can change this wavelength and do another measurement and so on. So, and at the end, we can get a full image, infrared image, spectral image of our sample. So, as I mentioned, so this our system combined both focal plane array detector and also QCL-based source. So that's you can get very fast infrared imaging of your sample. So now let's see what is the typical scenarios for measuring of this combined system. So scenario number one, so you pre-scan your sample with a QCL laser, just tuned to one wavelength, and create fast chemical image of this particular wavelength. And then you can find the point of interest, and then switch to FTIR and measure complete spectrum range in this particular area of interest. Scenario number two, so you use FTIR-based small area of imaging of the sample and figure out which wavelength is the most important for you to measure, which wavelength characterize the particular chemicals, and then tune QCL-based laser on this wavelength and do fast imaging of the distribution of this particular materials inside on your sample. This slide shows the comparison between a regular FTIR method and QCL-based imaging. So if you do a single wave number imaging, so it's about 110 times faster than FTIR. But if you do a sweep scan, so it's 14x times faster. Obviously, you get high advantage of using QCL-based systems on FTIR microscope. So one of the applications for this type of research is differentiation between cancerous and non-cancerous tissues. This is an example of imaging of lung cancer tissue. So there is some bands on the spectrum of this tissue. The band is 1240 and 1080 wave numbers are characteristic band for the cancerous types. And then we can plot the distribution or XY mapping of this band versus on the image, and you can see it here on the left side. So they're shown in red. That is show the cancerous the tumor position on this tissue. So there is a lot of different application for the imaging. So, but an example, you can characterize material composites, how homogeneous distribution of different ingredients on the material. You can also study adhesives. One of the important is you can do microplastics, so you can see its distribution of microplastics, the size, and also chemical identification of all microplastics on the plate. Multi-layer analysis of the films also can be done pretty easily. And 18 total reflectance of thin layers imaging also can be done. Moreover, so the next step, also Bruker developed dedicated QCL-based microscope. This is shown here, there is no FTIR part inside. It's just a QCL-based source and imaging detector. It's allow you to do fast imaging of all the tablets, tissue, and so on. There is some unique characteristics of this. Our largest field of view on an IR microscope, and on the safety, accessible, also system validation, and so on. And one of the advantages of this, it's pretty easy to operate. It doesn't require experienced person to run it. So when you start working on it, so it's done on a wizard base. So you can go through the wizard collect a visual image first, then select the area you would like to collect infrared, and then push the next button, and then automatically collect all the infrared images and do all the calculations. Can be done for tissues, cells, all the tablets. The flow, as I already mentioned, is straightforward. First of all, you do acquisition, automatically evaluation is done, and then you get automatic results. For example, is if you do microplastic, and shows you the how many microplastic is found, what's identification, and the size. That can be used, as already mentioned, microplastics or any other type of the measurements. And I'm a common conclusion. I think I convinced you that the laser-based infrared sources revolutionize infrared spectroscopy. In my opinion, so the QCL-based system will substitute FTIR system in the near future, at least in for many different applications. With this, I would like to switch to our next presenter, who just told you about what kind of QCL and broadband lasers are available from the Thorlabs. Thank you.
All right. Well, thank you, Sergey, for the introduction of laser-based mid-infrared spectroscopy. It's very interesting. So before I get into some technical details of our mid-infrared products, I would like to highlight a few things about Thorlabs. At the Thorlabs, we have many manufacturing competency, but here I will only mention a few related to mid-infrared light sources. Many of you may not know that we have a full 3-phi semiconductor manufacturer facility in Maryland, United States. And we design and manufacture various semiconductor lasers, again, chips, and even MEMS VCSEL module covering the whole wavelength range from near-infrared to mid-infrared. We also have a facility that can design and manufacture special mid-infrared fluoride fibers. With those capabilities, we offer a variety of laser sources, including QCL, ICL, QCL combs, and supercontinuum lasers, and ultra-low noise lasers, etc. Another thing that gives us a really advantage in manufacturing is that we are highly vertical integrated. We are capable at every level of manufacturing semiconductor lasers, including epi growth, wafer fab, chip design, packaging, testing, and all the way up to module production at the Thorlabs Maryland site. And we have a dedicated laser division that is focusing on integration of those components and manufacturing laser systems. So the combination of fiber, semiconductor, and the laser expertise is what enables us on our mid-infrared and long-wavelength IR product portfolio. So as pointed out by Sergey, mid-infrared and long-wavelength IR are very important wavelength ranges for spectroscopy. He showed that in this region, there are a few different types of light sources. Besides the difference in brightness, there are also some other key differences between them. Thermal sources like globars are commonly used. They are very inexpensive, but they're very low in brightness and has very low poor beam quality. On the other end, synchrotrons offers very high brightness, but they're huge, and you cannot. It's not portable. The light source is not portable and very costly. In the middle, supercontinuum light source can bridge the gap. They provide bright light source and excellent beam quality in a compact footprint. Furthermore, QCLs and ICLs are the only semiconductor laser sources, which means they are scalable in manufacturing. Even with a smaller footprint than supercontinuum lasers, they can offer high brightness emission and can be engineered for specific wavelengths, although the typical bandwidth is narrower. So why the mid-infrared is so important for spectroscopy? Sergey mentioned a few good examples of application. like chemical sensing in the liquid and IR imaging, I would like also point out a couple of key applications like trace gas detections. So because many gas molecules have strong fundamental fingerprint absorption lines in this wavelength range, as shown in this plot, measuring the absorption spectrum in this wavelength range enable trace gas detection with high sensitivity and high selectivity. The related applications include environmental monitoring like CO2, methane, ammonia detection, industrial process control, and medical diagnostics such as breath analysis. In this wavelength range, Thorlabs offers 4 complementary product families that together span the entire mid-infrared and long-wavelength IR spectrum. This plot shows the wavelength range they can cover. Our supercontinuum sources, the SC4500 and the long-wavelength IR supercontinuum, provide continuous broadband coverage. Our ICL and the QCL products can be custom designed to target any wavelength within their respective ranges, but with smaller wavelength bandwidth. We offer 2 different femtosecond supercontinuum laser sources. A little bit of history here. We started with the SC4500. It can cover continuously from 1 to 5 micron. However, based on the customer feedback on the wavelength coverage, we later developed this long wavelength IR supercontinuum, which is now commercially available. It extends the wavelength coverage all the way to 11 micron. They are both based on the femtosecond architecture. That means they are very low. They have very low short spectral noise. They are both all fiber-based design. That means they are environmentally robust. Most importantly, they are both compatible with FTIR spectrometer because they are high repetition rate. The supercontinuum lasers are fairly complex systems. I won't get into too much technical details on how they work. If we just look at the high-level architecture, both systems start with a 2-micron femtosecond pump laser. In a SC4500, the pump is coupled into indium fluoride fiber to generate the medium infrared light based on the current nonlinearity. For the long wavelength IR supercontinuum, we use modified indium fluoride fiber, followed by zinc germanium fluoride crystal. Extended the supercontinuum, extended spectrum into long wavelength IR based on the cascade intra-pulse difference frequency generation. In terms of a power output, the SC4500 can deliver more than 300 milliwatt output power, and the long wavelength IR supercontinuum can have output power higher than 80 milliwatt. If we look at the details of the SC4500, besides the feature I just mentioned, this supercontinuum laser has excellent spectrum stability and brightness and a high circularity beam. The repetition rate is 50 megahertz, which is much higher than the typical data collection rate of commercial FTIR. If we look at the power density of spectrum, we can see the amount of total output power 300 milliwatt. The power in the mid-infrared wavelength range, roughly from 2.2 to 4.2 micron, is more than 110 milliwatt. Well, this slide shows an example of experiment using SC4500 to detect multiple gas species in the mid-infrared wavelength range. On the left picture, on the top is the SC4500, and the bottom is a Thorlabs OSA 305 spectral analyzer. So on the right is the spectrum. The data show the absorption feature of methane and cyanide in the reference cells. By comparing the transmission spectrum with the absorption spectrum in database, we can detect if there's any target species present. On the other hand, if we look at the details of the feature of the long wavelength IR supercontinuum, we can see the biggest advantage of this laser is the wavelength coverage. With cascade DFG nonlinearity, the wavelength coverage extends all the way to 11 micron continuously. It provides more than 20 milliwatt in standard configuration. If you want more power, you can have the optional configuration that can get more than 80 milliwatt output power. Like SC4500, it also has very good beam spectrum, spectral stability, high brightness, good beam quality, and is fully compatible with commercial FTIR. All right, now let's switch gear. I would like to give a little bit of background introduction on QCL for whom are not familiar with this type of device. So we know that in conventional diode laser, photons are generated based on electron-hole recombination. Those lasers are called interband lasers. Unlike conventional interband lasers, QCLs use inter-subband transition within engineered quantum wells. We know that in a semiconductor quantum wells, the conduction band was split into subbands. In 1970s, scientists proposed using transition between subbands as a new method to generate photons. In this case, electron remains in the conduction band of the transition and can be reused in multiple transitions, in which electron cascade through multiple stages and generating the photon at each step. If we use this type of transition to make a gain medium and further design a laser with it, we create interband lasers. Inter-subband lasers. The first inter-subband lasers, or quantum cascade laser, was demonstrated in 1994 at Bell Lab. On the right-hand side is the band diagram of QCL. It is very complex. I will not get into the details of design, but one thing was to mention is that the photon energy in a QCL is determined by the energy separation of the subbands, which is mainly determined by the quantum well thickness. That means we can tailor the laser wavelength in a very wide wavelength range by change the quantum well design. Of course, there's some limitation. Due to the limitation of the semiconductor material selection or the conduction band offset, usually QCL can only work well in the mid-infrared wavelength range, or roughly from 3 to 12 micron. The left, right figure shows some wavelength of 5 Pro and a DAB QCL that we currently offer. There's no reason that we cannot make any laser, make a laser at any wavelength in the gap. It's just because we haven't done so, or there's not much of a customer request. Because of the intrinsic feature, so QCL is the only type of semiconductor laser that can cover the entire wavelength range in the mid-infrared range. And QCL is very compact. So if we compare the QCL with another type of compact light source at the mid-infrared, the globar, we can clearly see the advantage that QCL can offer. First, since it's a laser source, the QCL has very high spectral brightness. The spectral power density is 3 to 4 order of magnitude higher than globar. Second, also because QCL is a laser source, the emission is coherent. That means it has very good beam quality, and the beam can be focused on a very small spot. If we compare the highest power density one can get through a small pinhole, QCL have 10 to 12 order of magnitude higher power density than globar. Moreover, QCL can be fast modulated, and it has very fast response and a very little delay on turn-on latency. And these features make QCL ideal light source for high-performance spectroscopy. Now, we know QCL is one of the best light sources in mid-infrared spectroscopy applications. At Thorlabs, we offer both 5 Pro and DAB QCLs in multiple package types, from C-mount, D-mount to fully packaged devices like HHL and the TOCAN, all the way up to turnkey laser system. Here, I would like to highlight our so-called broadband QCLs the QF7900 HB, QF8500 HB, and the QF9200 HB. Each one has very broad emission compared to regular 5 Pro QCLs. The emission, the spectrum coverage varied from 400 to 800 nanometer. So one sample spectrum of a QF9200 HB is shown here. You can see that one laser can cover the range from 8.4 micron to 10 micron. Moreover, collectively, 3 of them can cover continuously from 7.7 micron to 10 micron. Of course, we have other standard 5 Pro QCL at wavelengths from 3.8 micron all the way to 10 micron available on our website. Typically, their spectrum coverage less than 100 nanometer. Last but not least, our 5 Pro QCL products have been proven with very good spectrum stability and reliability. Here's a plot of a laser spectrum of a 5 Pro QCL collected 10 times and superimposed together. The 10 spectrum overlapped on each other perfectly. With the high resolution data, we can resolve the 5 Pro mode, and we can see clearly the mode position and intensity did not change with time. We also did a live test study on QCLs many years ago, and our 5 Pro QCL have more than 800,000 hours lifetime at a typical operation condition. So with a quick overview, we offer both QCL and ICL in a wide range of form factors. Chips on sub mount, C mount, D mount, HHL package, TO cans, and turnkey lasers. The power level exceeds 1 watt for some 5 Pro QCLs, and the wavelength span from 3 to 12 micron. It was mentioned that we also provide a custom QC GaN chip at different wavelengths for external cavity laser system. On the bottom right plot shows the GaN profile of different GaN chips we are making, covering different wavelength bands in the 3 to 12 micron wavelength range. Before the end of the talk, I would like to mention that we also offer a full ecosystem of mounts and drivers to support integration. We have water-cooled HHL mount, TEC-cooled C mount, and the TO-CAN mounts, benchtop drivers across multiple power level. This ensures stable and safe and high performance operation of QCLs and ICLs. That's the end. I would like to thank you for your time and attention. Thanks.
Perfect. Thank you, Feng, and thank you, Sergey, as well. Yeah, that was great. I really appreciate, I said in the earlier session, I really appreciate the convergence and the 2 distinct takes on the same problem coming from the spectroscopic techniques perspective and also from the laser technology perspective. Yeah, I hope everyone was able to learn something from that. And thank you again to the attendees also for taking the time to listen. I did see that the participation in the Q&A was good, so we have a number of questions queued up for you. I'll do my best to kind of go back and forth between speakers asking questions. Starting actually going back to Sergey and the spectrometers, I'm actually going to start you with a multi-parter regarding time resolution. So can you comment a little bit about the limitations of the acquisition rates of the spectrometers and what the trade-offs are? And then can you make any sort of comment on the time resolved performance compared to techniques like step scan? The listener was asking in the context of looking at something like a dynamic process like fast diffusion.
Okay, yeah, sure, yeah. We use a quantum cascade laser as a continuous source, not a pulse source. So basically, this is just a very bright source. And limitation is the same as you do a regular spectroscopy with a step scan spectroscopy. So your limit will be the response time of your detector, which is currently like few nanoseconds. So, but you get obviously better signal to noise because you use a brighter source on the microscope. But still, your limits will be response time of your detector. Okay.
Thank you. Feng, you had mentioned a couple times in the context of both the semiconductor lasers, the ICLs, QCLs, but also in the supercontinuum, the importance of the beam quality. Can you expand a little bit about what you mean by the beam quality and how that shows up in these applications? I think you kind of ended to talk a little bit about the relative brightness.
Yes. Usually, coherent light source has a better beam quality, and that means you can focus the light into a smaller spot. That means you can have higher light intensity in the spot, and that means one thing, you can have better spatial resolution in the microscope application, or you can have deeper penetration or better signal noise ratio. In some scenario, you may want to use fiber to guide the light to your sample in certain application. And coherent light or good beam quality can help you to couple more light into the fiber. Then you have more light in the fiber and better signal noise ratio, etc.
Perfect. Thank you. Sergey, back to you. You had given an example of tissue imaging. Can you comment and expand a little bit about the requirements of tissue imaging, specifically the spectral resolution that you were showing in the sort of spectral resolution that might be typical for an application like that? The requirements of spectral resolution.
Okay. Yeah. Typical requirements like 4-wave number resolution is good enough for all the condensed matter measurements. So let's say that's 4-wave numbers is like this is very standard for such measurements.
Thank you. Feng, a couple fundamental laser questions, I guess following on the beam quality. This one is about the differences between ICLs and QCLs. Can you go into a little bit of detail about what those differences are, but importantly, what the trade-offs are and limitations in terms of what's achievable with those two technologies?
Okay. So ICL is also a semiconductor lasers, but it is using the so-called interband transition, not intersectband transition. On this end, like it's similar to traditional laser diode, but there's no p-doping in the ICL. So the hole is generated by so-called semi-metallic interface. So because of that, you can stack multiple stage together to have high gain, similar to QCL. So that's why you have the cascade in the name. But because of the lasing, like the intrinsic mechanism, the wavelength coverage is a little bit shorter than QCL. So it covers very well from 3 to 5 micron. There's a researcher working on like even longer wavelengths. But if you compare the ICL and the QCL, typically ICL has a shorter wavelength and a little bit lower output power, but it has a nice like low threshold current and the voltage. That means you have a lower power consumption. The biggest difference is like the wavelength coverage and power level and the power consumption. In terms of a limitation, I would say if you want to access 3 micron, 3.5 micron is definitely the ICL. You want to use ICL, it's easier to make. But if you want like high power, like watt level output power, then you probably want to use a QCL. Especially at a long wavelength, like, say 6 to 10 micron wavelength range. QCL is probably the best option.
Perfect. Sergey, there's a question. Can the IR microscope be used for emission studies?
Okay, sure. That's, of course, you don't need a quantum cascade laser for this. But in case if you developing a new sources, so you would like to measure emission, and if your sample or your emitter is small, so then you can put it in a microscope, and we have a special option for emission option on the microscope. You can measure not just on the emission, but you also can map emission of your sample.
Thank you. A couple multi-parter for you, Feng, on the QCLs. The first is using the supercontinuum. So this is going to tie to the QCLs. Trust me. Is using a supercontinuum similar to using a frequency comb? And I know you have some expertise here. So do you also have any comment on how what comb characteristics are important and how that fits into the greater QCL landscape?
Well, QCL comb is I would say, in certain ways similar to supercontinuum as like multiple wavelengths emission, but so far my understanding is people tend to use, QCL comb as in a dual comb spectroscopy kind of application. You're trying to use the coherence between the combs and then generate like the beating between two combs. Not sure about the supercontinuum in this case. So my understanding is maybe it's not so easy to integrate it with FTIR with the QCL comb. Probably not as easy as a supercontinuum laser source.
Right, so supercontinuum is more integratable into a commercial system, but the supercontinuum doesn't have the discrete comb lines that a comb would have to give those related advantages.
Right, and another difference probably is QCL combs are still as narrow a bandwidth, not as broad as supercontinuum.
And then related as well to the QCLs, and it is tangentially related to combs, but this isn't specified for combs. You mentioned at the end the modulation capabilities, direct modulation of QCLs. What is possible? What are the sort of the fundamental limits, do you think, in terms of what you've observed or been able to achieve in terms of direct modulation?
Well, this is an interesting question. So QCL itself, using the intersegment transition and because of the lifetime is really short, that means intrinsically can be modulated very fast. So people, there are researchers who are interested in the like free space communication using QCL. So we are developing some sort of high-speed HTL package. We observe like at least you can modulate the laser up to gigahertz level without any problem. We just limited actually by the circuitry of the package instead of the chip itself. Certainly, there's some limitation on the chip itself because usually QCL is very it's fairly long. The large area causes large capacitance, in the chip, so that may have some limitation of modulating speed, but that potentially can be improved with certain design. Yeah.
Thank you. Going back to the spectrometer, Sergey, you have direct experience integrating both QCLs and supercontinuum now into your instruments. Are there any concerns or considerations that a user would have if they were retrofitting a Bruker instrument with such a bright source?
No, I don't see any concerns. So usually you use these bright sources for low throughput applications, so the beam will be attenuated by the sample. So I don't see any concern about this. So it should be no problem. Yep.
And then I see a question about the lifetimes of the supercontinuum laser. So, and if there are issues with water absorption to the fibers, I can actually answer that quickly. So the supercontinuum lasers are in some cases employed into industrial settings where they're running 24 hours a day for various QC processes. The original SC4500 was an all-fiber design. It's very robust. And we've now we're approaching a decade of having produced these. It's all based on the fluoride fiber we produce in-house, actually across the street from where I'm sitting. And we have not seen issues with water absorption. They've proven to be very reliable over long-term usage. Related to the Hyperion microscope, Sergey, what's the limitation on the spot size, practically speaking, and are there recommendations regarding the objective that you use for if you assume normal incidence of light onto the sample?
Well, the spot size is limited to diffraction limit, so that's or special resolution. Typically, that you can go with a special resolution as good as maybe 5 to 10 microns. That's on mid-IR spectrum range. Yeah, and typically we use 15x or 36x objectives. So with 15x, you have it's about 1 inch working distance, so you can put additional like samples or cryostat and so all the things. Yeah, but that's our standard. So.
Feng, the QCLs you had, in the context of today's talk, you were mentioning that these are broadband sources. I mean, not as broad as a supercontinuum, of course. But the question is, shouldn't lasers be narrow? Why are these broad?
So laser is usually considered narrow light source compared to globar or this supercontinuum light source. Some of the laser like DAB lasers, like they have feature to lock the wavelength. So there's only one wavelength. They're super narrow. In certain application, you need a narrow line width. But just regular 5 Pro lasers, because the gain profile is relatively broad compared to DAB wavelengths. So there are multiple 5 Pro mode can lace, so relatively they are broad. The typical bandwidth or emission bandwidth is roughly around 50 to 100 nanometer wave number. That's the typical emission bandwidth. The 3 so-called broadband 5 Pro QCL, special designed QCL, the emission bandwidth is much broader than typical 5 Pro lasers. So we are trying to explore the potential application with those devices. See if especially for this mid-IR spectroscopy application, combining those lasers with FTIR would be, probably super helpful.
Thank you. Actually, I'll piggyback off of that. You're describing there a number of different laser designs that you're completely in control of in-house through the vertical integration. From the way you describe that, does that mean that these lasers are broader use case in the sense that you're providing gain material, chips, et cetera, to laser vendors outside of Thorlabs as well?
Yes. Yes. Well, we do have customers, purchasing, gain chip from us and all laser components like a chip on sub-mount and further integrate into their systems. So we welcome this kind of collaboration.
And does that involve special material design to meet customer wavelength requirements?
Yeah, certainly. Yeah, we have made a lot of custom designed QCLs on both GaN chip and regular 5 Pro or even DAB QCLs. Yeah.
And then I think we have one last one for Sergey. You mentioned in passing working with customers on advanced applications, and you hinted at a demo room or some sort of application space. Can you expand on that? What you're referring to there, and maybe an example of an application?
Sure, yeah. We have a big demo lab in our facility in Billerica, Massachusetts. So we have all the microscopes, including Lumos, Hyperion II, Ilium, and vacuum, non-vacuum system, and small systems. So if you have good samples, I prefer challenging samples to run, you are welcome to our lab, and then we can run samples and make fun.
Perfect. Thank you. And actually, with that, we actually got through the questions. So I think that's all the time we have for today anyway. That runs us out just about right. So I'll extend another thank you to, first and foremost, the audience for participating, taking the time to hear us today. And then thank you also, of course, to Sergey and Feng for the time, for the presentation. This was really great, and good engagement from the audience as well. Everyone, I hope you found it informative. We will post this on the Thorlabs website, so you'll have access to the recording. If I didn't get to your question or you have one later, you can certainly reach out. We can answer those as well. So please don't hesitate to reach out. We're happy to help. And thanks again. We hope to see you at the next event.
Thank you.
Thank you. Bye.
Yes.